Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to the 11th lecture of Mechanics of Solids. Today we are going to discuss one of the most important topics in this subject, that is bending. In this lecture we'll start from the very basics of bending, that is basically from the construction of the shear and moment diagrams. We'll discuss one of the easier methods of constructing shear and moment diagrams, that is the graphical method. And in this lecture we are going to discuss a lot of examples. The reason being, bending is a very central concept in mechanics of solids as well as for the whole structural engineering realm. So it is quite necessary to understand these basic concepts in a way that will help develop understanding for future subjects or for future courses. Okay, so bending is the main concern in beams. So mostly when we are discussing bending, we are focused on the structural elements that act as beams. Members that are slender and support loadings that are applied perpendicular to their longitudinal axis are called beams. In general, beams are long, straight bars having constant cross-sectional area. Often they are classified as how they are supported. For example, a simply supported beam has a hinge support at one end and a roller support at another end. A cantilevered beam is having a fixed support only at one end. Fixed support means that it is not allowed to translate in either horizontal or vertical direction, and it is not also allowed to rotate in any direction due to this fixed support here. And then we have the overhanging beam. The overhanging beam has a has one or both of its end freely extended over the supports. As you can see here, that this end is freely extended over one of the supports, so it is called an overhanging beam. Beams are considered among the most important of all structural elements. They are used to support the floor of a building, the deck of a bridge, or the wing of an aircraft. Also, the axle of an automobile, the boom of a crane, even many of the bones of the body act as beams. We have discussed what a beam is and what is the purpose of the beam in different structural compositions. Now we can discuss the mechanics of the beam. Because of the applied loadings, beams develop an internal shear force and bending moment that in general vary from point to point along the axis of the beam. In order to properly design a beam, it therefore becomes necessary to determine the maximum shear and moment in the beam. These shear and moment functions can then be plotted and represented by graphs called shear and moment diagrams. The maximum values of shear and moment can be obtained from these graphs. Since the shear and moment diagrams provide detailed information about the variation of the shear and moment along the beam's axis, they are often used by engineers to decide where to place the reinforcement within the beam or how to proportion the size of the beam at various points along its length. For example, consider this beam. From A to B, the load is continuously varying due to this triangular load, and thus the shear will continuously vary in this region. From B to C, there is no applied load and there is no support, so the shear will remain constant within this region. Then from C to D, again we are having an applied support here, so the shear at this point will change, and the bending moment will vary along the whole length of the beam. Why will this happen and how can we determine these things? We will discuss all these points in the upcoming slides. Before discussing a method for determining the shear and moment as functions of x and later plotting these functions, shear and moment diagrams, it is first necessary to establish a sign convention so as to define positive and negative values for shear and moment. The choice of sign convention is arbitrary. However, in these lectures and often in general engineering practice, the following sign convention is used. The positive direction is taken when the distributed load acts upwards on the beam. The internal shear force acts um, clockwise. The internal shear force causes the clockwise rotation of the beam segment on which it acts, and the internal moment causes compression in the top fibers of the segment and tension in the bottom fibers of the segment. Loadings that are opposite to these are considered as negative. I'll repeat this thing for further clarity. Like, if the beam is curving in this direction such that its top fibers are in compression and its bottom fibers are in tension, then we say that this is positive bending, and the shear force at this location will be directed in downward direction, and the bending moment at this, if we are taking a section from the left, then the bending moment, the positive bending moment here will be anti-clockwise, and the positive shear will be downwards. However, these sign conventions become opposite if we are taking a section from the left. Here, the shear that is upward will be that is directed upward will be considered positive, and a bending moment that is directed clockwise will be considered as positive. So remember this thing, that we have to consider the overall direction of the rotation of the beam, as well as from where are we taking the section while using a particular sign convention for a particular problem. And bending moment diagram can be constructed using the following procedure. First of all, you have to determine the reactive forces and couple moments acting on the beam. For example, if you consider this beam, then before beginning any analysis, we have to determine the vertical reaction at location A, the vertical reaction at the support C, as well as the horizontal reaction at the support A. In this case, the horizontal reaction at support A will be 0 because we are not having any kind of horizontal loading here. With that said, the next step is specifying the shear and moment functions. For this purpose, we have to specify separate coordinate axes having an origin at the beam's left and extending to regions of the beam between concentrated forces and or coupled moments, or where there is no discontinuity of distributed loading. Like, for example, if we have to describe sections in this beam, we'll take our first section here, our second section here, where the loading is ending, or sorry, or where there is any change, like loading is ending at the point B, so our second section should be between point B and point C, and our third section should be between point C and point D, because here we are having a support and we are also having a load at the end. So it means that there will be a change or a variation in moment and shear within this location as well. Okay, our final step is to construct the shear and moment diagrams. Once we have the functions, we can simply plot the shear and moment diagrams by plugging in the values of the x that we have considered. These things may seem too much abstract at this point, but all this will become clear in the example as we are going to discuss on the next slides. So in this example, we have to develop a shear and bending moment diagram for this beam. We can see here that this is a simply supported beam with a hinge support at left end and a roller support at the right end, and a uniformly distributed load is applied along the length of the beam. Before determining the shear and moment functions, as I have already mentioned, we have to determine the support reactions. In this case, determination of support reaction is quite simple. Just take summation of y, and if we take summation of y, summation of forces in the y direction, and the summation of moments, we can easily determine that this distributed load WL acting at the center of this beam is equally divided between these two supports. So the reaction at support A, for example, if you call it A, will be WL by 2, and similarly the reaction at support B, for example, if you call it B, will also be WL by 2. Now once we have the support reactions, we can determine the shear and moment functions. So for determining the shear and moment functions, as I have already said, we have to take a section. How can we take a section? Here we are having a continuous loading throughout the length of the beam, so we need to take only one section here. We'll take a section, for example, at this point. Let's say we're considering the origin at A, so this is A, and any segment along this direction will have a length x. Now to determine the shear force at this point x, we have to again take the summation of forces equal to 0. If we consider the upward as positive here, then WL by 2 will be positive minus WX. WX shows the intensity of the loading at the center of the segment of length x, minus VV is our shear force, that is the unknown force here. And by solving this equation, we have come across this relation for the shear force. Now how can we determine the function or the relation for the bending moment diagram? For that, we have to take summation of bending moment while considering the anti-clockwise as positive. So if we take a look here, this this vertical force here, or this reaction force here, is actually causing a clockwise moment. A clockwise moment. This downward force here is causing an anti-clockwise moment. Always try to use right hand rule while determining these forces. Right hand rule states that extend your right hand in the direction, or the fingers of your right hand in the direction of your moment arm, and then curl your fingers in the direction of the force. So in this case, you have to curl your fingers in the downward direction, and this curling of fingers will show you the direction of rotation, which is anti-clockwise in this case. Thus we have taken this minus WL by 2x plus so on and so forth, the bending moment for the loading, and then again the bending moment or the internal moment of the segment has been taken as positive. Thus this comes out as m is equal to W by 2 into Lx minus x square. This is the relation for the bending moment. And the shear diagram can simply be plotted by putting different values of x in the relations that we have determined. Okay, if we want to determine the point of zero shear, we just have to put 0 in the relation for the shear, and we have determined the point or the location where the shear will be 0, that is exactly along the mid length of the beam. From this x is equal to L by 2, we can then determine the value of the maximum moment. We have discussed this thing, and we'll consider this thing in some more detail in an upcoming lecture, that shear force is actually a slope of the moment diagram. Thus, from calculus, we know that a function has a minimum or a maximum value at the point where its slope is 0. So if shear is 0 at this location of L by 2, then this means that moment will be maximum at this point. Thus, if we plug this point in the moment equation, we can determine the maximum value of moment in a simply supported beam under uniformly distributed loading. That comes out as WL squared by 8, or where W is the intensity of the applied load. So now we are on our second example. Now we have to draw a shear and bending moment diagram for a beam on which there is a combination of uniformly distributed as well as uniformly varying load. So in the first step, when we have to determine support reactions, we'll divide this load into two portions. The one portion that will be applied as a rectangular load is of 2 kip per feet, and the second portion is of 6 minus 2, 4 kip per feet, 4 kip per foot, and that is the uniformly varying load. For the uniformly distributed load, its centroid will be coincident with the centroid of the beam, or with the center point of the beam along its length. Thus we have 2 into 18, 36 kip load that is being applied at at a distance of 9 feet from the left end of the beam, or also from the right end of the beam. And then when we are determining the centroid for this triangular load, we have to consider this thing, that the centroid for this triangular load will be at a distance of 2 by third of the length of the beam from this end, and 1/3 of the length of the beam from this end. So this 36 kip load will be applied at a distance of 12 feet from the left end, or 6 feet from the right end. When we have to determine the reactions, we'll take the summation of forces as well as the summation of moments. The summation of forces and the summation of moments will give us the two unknown reactions, and they come out as 30 kips and 42 kips. How have we done that? I'll just write this so that it can be made clear. 36 plus 36 will be equal to the summation of the unknown forces at location A and at location B. And for example, and now we are taking the summation of moment in the next equation. We are taking the summation of moment at location A. Please ignore my writing. If we take the summation of moment at location A is equal to 0, it will be simply 36 into 9 plus 36 into 12 is equal to by into 18. And by solving that equation, we'll obtain 42 kip as by, and then plugging that value in this equation, we can obtain 30 kip as the ay, or the reaction ay. Now we'll move towards our next step, that is the determination of the shear and moment functions. For this, we'll have to take here a segment. So the load, although the load is varying along the length, but there is no discontinuity in the load along the length. So we can take only one segment in this case. If we are taking one segment, and then again here is consider this segment, we have a 30 kip load on the left directed towards upward direction, that will be written as positive for the for in the equation for the shear. Then we have a minus 2x. Yeah, 2x means that 2 multiply the uniformly distributed load is being multiplied by the length of this segment minus 2x, and then we have the uniformly varying load, and for the uniformly varying load we will have to use the principle of similar triangles to determine its intensity at a location x. So if we have if we have the height of this as 6 minus 2 is equal to 4 here, and and we know that the length of this segment is x and the length of the whole of the segment is 18, we can use the similarity of triangle as 4 divided by 18 will be equal to the unknown loading at x, which is here, and let's consider it as y, and it will be divided by y by x. So this unknown y will become as y is equal to 2 over 9 by x. So the unknown loading, or the loading due to this uniformly varying load, is usually determined by applying the principles of similarity of triangles, and thus we have this here minus 1 by 2 into 4 into x by 18 into x minus v. So again I have only determined here the value for this, you can say the value of the height of this triangle, but when we have to apply it as a force, we have to consider the whole area of this triangle, which will be minus 1 by 2 into 4 into x by 18, which we have just done, which comes out as 2 by 9x, and then minus v is the unknown shear force here, and thus we have obtained an equation for the shear force, or a relation for the for determining shear force along the length of this beam. For the summation of moments, we'll just simply take these forces and multiply them by their momentum, by their respective momentums. So the moment arm for the 30 kip force will be the length of this segment, which is x. The moment arm for the uniformly distributed load will be half of the length of the segment, and moment arm for the uniformly varying load will be 1/3 of the length of this segment. And again m is the unknown bending moment, and in this way we have obtained this equation for the bending moment. Previously determined equations, we can draw the shear and bending moment diagrams. We can see here that for the combination of uniformly varying load and a UDL, we have a 2-degree equation for the shear diagram, and we have a 3-degree equation for the bending moment. And once we have the shear, and we know then we can determine the location of zero shear, and from the location of zero shear we can then determine the value as well as the location of the maximum bending moment. Okay, before delving into more complex methods of constructing shear and moment diagrams, let's consider this, that why are we doing this? Let's get back to this basic reason. In this diagram, you can see that the failure of this table occurred at the brace support on its right side. If drawn, the bending moment diagram for the table loading would indicate this to be the point of maximum internal moment. So, this a very basic thing such as failure of a table is dependent on this thing, on shear and bending moment and all these things. So we can see this, that these abstract concepts have a very basic and fundamental role in every structure that we see around us. All the structures are stable because they have been made stable by applying these principles. So never underestimate the understanding or the practice or the exercise of getting a understanding these principles to become a better engineer as well as a better observer of the phenomena around you. In cases where a beam is subjected to several different loadings, determining shear and moment as functions of x and then plotting these equations can become quite tedious. So, in this discussion, we are going to take a look at a simpler method for constructing the shear and moment diagrams, a method that is based on two differential relations, one that exists between the load and shear and the other between shear and moment. Derivation of the method, that is the graphical method for constructing shear and moment diagrams. For purpose of generality, consider the beam that is being shown here. This beam is subjected to an arbitrary loading. A free body diagram for a small segment del x of the beam shows that this segment has been chosen at a position x where there is no concentrated loading or couple moment. So the results that we will derive for this arbitrary loading are not applicable to the influence of or the effect of the results due to this concentrated loading. All the loadings on the segment act in their positive directions according to the established sign conventions. Also, both the internal shear and moment acting on the right face of the segment must be changed by a small amount in order to keep the segment in equilibrium. The shear and moment at this point are not exactly equal to the shear and moment at this point because we are having an applied loading on this segment, and this shear and moment must change to take into account of this applied loading on this segment. Okay, the distributed load has been replaced by a resultant force Wx into delta x, which is the length of the segment. If we apply the equations of equilibrium in the segment, we can come up with this equation with these equations. If we apply the summation of forces in the y direction, v plus wxv is the shear force on the left direction. This is the applied loading, and then we have the shear force on the right direction, which is in the downward direction to keep the segment in equilibrium. And we come up with this differential equation where the change in the shear force along this segment is actually equal to the applied load multiplied by this distance, applied load intensity actually, multiplied by this distance. If we take the summation of moment at point O, we can just apply the respective moment arms uh, to these loadings, and thus for this left-handed shear, for the shear on this left face, the moment arm is delta x. The moment arm for this applied loading is actually k into delta x. K basically shows the distance, uh, the fraction that can be used to indicate the distance of this resultant force and the end of the section. And then we have the m plus delta m, which is actually the moment on the right side. Dividing by delta x and taking the limit as del x approaches 0, the above two equations become, if we divide these two equations by delta x and take the limit, we come up with these equations which shows that the slope of the shear diagram at each point is equal to the distributed load intensity at each point. It is very crucial to remember this point, that the load diagram is actually basic slope of the shear diagram, and a shear diagram is equal to the slope of the moment diagram. So we'll use these two basic equations to develop our graphical method, and these concepts will also be used in further other developing other methods and concepts in the bending. Apply the concept developed on the previous slide to a beam that is being subjected to a uniformly varying load, which is having the maximum intensity of WB. We can see here that the distributed loading is negative because it is directed downwards, and therefore the shear diagram will be a curve that has a negative slope increasing from 0 to minus WB. In a similar manner, the second equation that was developed on the previous slide stated that at a point the slope of the moment diagram is equal to the shear. So the shear diagram starts at plus VA, decreases to 0, and then becomes negative and decreases to minus WB. The moment diagram will then have an initial slope of plus WA, which decreases to 0 here when the slope is becoming 0 and the moment is maximum at this location. Then the slope becomes negative and decreases to minus WB. The equation developed in the previous slide can also be written in the integral form. If we take an integral of the differential equation, we can find that the change in shear is actually equal to the area under distributed loading. So the area under this loading will show the change in shear between the points C and D, and area under this shear diagram between the points C and D will show the change in moment between the points C and D. Since these equations are not applicable to the points where a concentrated force or coupled moment acts, in the next slide we'll consider the case of concentrated forces and moments. A case where a concentrated force and a concentrated moment is being applied on a small segment of length del x. So if we take a summation of forces here, we'll determine that V, and if the applied force is also upward, V plus F minus the shear on the right side, and this V and V will cancel, and we'll come up that the change in shear is actually equal to the applied force. So if the force F is directed upwards on the beam, the change in shear is positive and it will jump upward. If F acts downwards, the jump or will be downward, or the shear will actually decrease. Likewise, if we are applying a moment and the moment is applied clockwise, the change in the bending moment along this segment will be positive and it will jump upward. And if the applied moment is anti-clockwise, then this jump will be downwards. So it is very easy to consider the concentrated forces and moments just by introducing their values with the correct sign convention in the equation that we are normally using for the determination of shear and moment along the segment. Now we are considering some examples on how can we use the graphical method for constructing shear and moment diagrams. We have to construct a shear and moment diagram for this beam that is being subjected to two concentrated forces at two different locations along its length. This is a fixed beam, so if we want to determine the reactions at this location, I will call this location as A. Summation of forces will show that the vertical reaction at this location will be 2p, and the moment at this location will be, since this is causing a clockwise moment, and this force is also causing a clockwise moment of P into 2L, and this is causing a clockwise moment of P into L. So the resisting moment at this location will be 3PL. It will be actually the combination of these two moments. Now if we have to construct a shear diagram, we'll have to consider two segments. One segment will be here before the application of this load, and the other segment will be here after the application of this load. Before the application of this load, we can see here that there is no distributed loading, so the slope of the shear diagram will be 0. The force the force P at the center of here we are having a support reaction of 2P, and there is no loading in between, so the shear diagram will have a 0 slope. And then, as we discussed on the previous slide, that the shear force will jump downward if we are having a concentrated force. So this 2P will jump downward equal to the amount of this applied load, which is P here. Then again it will remain constant because we are not having any loading between these two segments, between these two loads. And at this end point of the beam, it will again jump downward equal to the amount of this applied load, which is P. So this is our shear diagram. And in order to plot the moments at the using graphical method, just start from this moment. Since this is being applied counterclockwise, the resisting moment will be clockwise, and thus if resisting moment is clockwise, we have to consider it as negative. The moment diagram consists of two sloping lines, one with a slope of plus 2p and the other with a slope of and the other with the slope of plus p. The value of the moment in the center of the beam can be determined from the area under the shear diagram. We know that the change in moment along this length will be equal to the area under the shear diagram. Thus, in order to determine moment at the center point, we'll have to take the moment at this x is equal to 0, which is minus 3pl, and then add it to the change in moment, which is the shear area under shear diagram, which is 2p into l, and thus the moment at the center of the diagram will be equal to minus pl. And similarly, we can apply the same concept to determine moment for the rest of the length of the beam, but we can simply use a straight line as well to connect this minus pl to this point 0, because moment will become 0 at the end point of the beam, as we are not having any kind of support at this point. So in this way we have constructed shear and moment diagrams using the graphical method. Okay, now we are on our fourth example of this lecture, in which we have to construct shear and moment diagrams for the beams shown here. This is also a fixed beam that is being subjected to a uniformly distributed load, and in another figure we are having a beam that is being subjected to a uniformly varying load. Let's first consider the beam subjected to uniformly distributed load. Again, first we have to determine the support reactions. Just fix these steps in your mind. You have to start from determining support reactions. So this applied loading, just because we're having a fixed support here, so we'll have the vertical reaction as well as the moment. Our vertical reaction will just be equal to the intensity of the load multiplied by length, W naught L, and the moment will be equal to the moment due to this load, which is for which you have to find the resultant, which is W naught L, multiply by this distance, which is L by 2, because UDL always act on the center of the span. The resultant of UDL always act on the center of the span. So W naught into L by 2. Now we have to construct a shear diagram. The loading is negative, thus the slope of the shear diagram will be negative. We'll start from W naught L, and since we have a UDL, this shear will continuously decrease, and shear will be a this will be a 1 degree shear diagram. Like, we cannot have a constant shear diagram here, because, or a shear diagram with a slope of 0, because we are having a uniformly distributed load here. From this shear diagram, we can then go towards the moment diagram. We'll start from the negative moment here, the negative moment where that was being applied at the support, or that is present at the support, and then we have the slope of this moment diagram will decrease slowly, and this will be a 2nd degree moment diagram, because we are having a 1 degree shear diagram. So the slope will decrease slowly until it reaches 0 at the end point. So this is a very simple and easier method to construct shear and moment diagrams. Now consider the beam that is being subjected to uniformly varying load. Again, we have to determine the intensity of the load, or the vertical reaction here, which will be equal to W naught into L by 2, because we have to take the area under the loading diagram, which is 1 by 2 into W naught into L, this whole length. And again, we have to take moment, but here the moment arm will be L by 3, because the resultant of the triangular loading acts as at a location which is 1/3 from the initial point of the beam, from the origin. So if we multiply this W naught L by 2 into this moment arm of L by 3, we'll come up with the moment of W naught into L square by 6. Now we have to move towards the shear diagram, and since this loading is a 1 degree diagram, or it is having a slope, it is actually having a slope, a constant slope, we'll have a 2 degree shear diagram and a 3 degree moment diagram. The rest of the procedures of determining values is the same, that you can simply determine the value of moment at any location by equating the moment, by taking summation of moment at the initial or the starting point, and then adding it to the change in moment within that segment. So here the change in moment is just equal to the area under the shear diagram, but determining area under the shear diagram for 2 and 3 degrees is a bit difficult, so we are having some of the easier procedures for determining that, which we may discuss in our upcoming lectures. But for the discussion here, it is worthwhile to understand how can we determine these, how can we construct these diagrams for these simpler cases of loadings. Now we are considering our more concrete example with values to the applied loadings. Here we are having a cantilever beam, again a fixed beam with a combination of distributed loading and a concentrated load. Again, we have to begin our calculation with the determination of the support loadings. So if we have this applied 1.5 into 2, 3 plus 2, 5. So on the whole, we are having a 5 kilonewton force acting on this beam, and thus we'll have a vertical reaction of 5 kilonewton. And if we have a moment of 1.5 into 2 into 1, that will be 3, and plus moment of 2 into 4, 8, and thus the reaction moment at this location will also be 11 kilonewton meter, sorry. And here these applied loadings are causing a moment or causing an anti-clockwise moment, thus the resisting moment will be clockwise, and thus we have a clockwise moment here. Now we can go towards the construction of shear diagrams. From x is equal to 4 to x is, if we have to determine the shear at this location, how will we begin? Just consider the shear at this location of x is equal to 2, and then the change in shear in this segment. So the shear in this segment from 0 to 2 will simply be upwards 2 kilonewton, and since we consider downwards as positive in shear, if we are taking a segment from left, then we'll consider this upward shear negative. And similarly, we'll have an upward shear due to this applied this negative loading, minus 1.5 into 2, and the summation will be minus 5. So we'll have a shear force just to the left of this support that will be equal to the minus 5, that will be equal to minus 5 kilonewton. So we'll begin our shear diagram with a slope, with a zero slope, right? But with a negative constant of minus 2, and then at point x is equal to 2 meter, this shear diagram will change its shape because loading is changing its form from concentrated loaded to uniformly distributed load, and thus we'll have a shear of a negative shear, a shear with a negative slope of 1 degree. If we are going towards a moment diagram, again we'll start from 0 because there will be no moment here as it is a free end, and we'll have to determine moment at this location, which will be equal to 2 multiplied by 2 minus 4, and the moment at this location where of the fixed support is actually equal to minus 11, that is the moment at the fixed support. Again, notice this thing, that where we are having a constant or a zero slope of the shear diagram, we are having a moment diagram of 1 degree, and where we are having a shear of 1 degree, the moment diagram will have a 2 degree slope, will be a 2 degree function, right? It will be it's a kind of parabolic function. You have to keep these things in mind because these concepts will be repeated in any case in whenever you're trying to understand any case of bending. Okay, so now we are on our third example of this, or actually fourth example of this graphical method for constructing shear and moment diagrams. Here we are having an overhanging beam, and interesting case is that the load is being applied on the overhanging part of the beam. How can we determine the shear and moment for this particular case? Let's see. Again, this problem will become very simple if we start from determining the support reactions. You have to take summation of forces. Summation of forces means AY plus BY is equal to 4 into 2. I'll write it here for clarity. AY, just consider that a Y with the B as well, and this will be equal to the 4 into 2, thus 8 kilonewton meter. Sorry, 8 kilonewton. Yeah, 8 kilonewton. And if we are taking the summation of moment at location, you can say Y, and we are considering B as upwards here, so it will cause an anti-clockwise moment, and this will cause a clockwise moment. So from the calculation, B will come out as 10 kilonewton upwards, and AY will come out as 2 kilonewton downwards. This is because the load is being applied on the overhanging part, so this couple, due to this loading, will be balanced by a couple or an opposing couple due to these loadings. If we have to construct shear diagram, again from point A to point B, we can have a shear with a constant slope, and at location By, the shear will change its location, or a shear of 10 kilonewton will get added to this -2, and we'll have 8. And then from point B to point C, or from that to the end point, we'll have a shear of constant slope due to this UDL. If you have to determine moment, the moment at this location A will be 0, and we can determine the change in moment by this area under the shear diagram, which is actually equal to -2 into 4 minus 8. Thus the moment value of moment at this location will be -8, and then from this to this it will be a 2-degree diagram that will decrease to 0 from the point B to the end point. Example of this lecture. I hope you have grasped all the concepts of this lecture. Let's delve into our last example before ending. Here we are having a simply supported beam that is being subjected to a uniformly varying load. Again, the process is very simple. You have to first determine the support reactions using summation of forces and summation of moments. And for the shear diagram, we have to consider this thing here, that we'll start from the value of shear that is here, that is positive shear of 240 pounds. And because we are having a uniformly varying load, we'll have a shear of decrease, a shear diagram of 2 degrees slope. And then we have to determine where the shear will be 0. And how can we determine this thing? We can determine this thing that by using summation of forces equal to 0, and we want the summation of 240 pounds and this applied load to be equal to 0. And thus in this way we have obtained that x is equal to 6.93 feet, that the shear will be 0 at 6.93 feet. And then simply we can decrease the value of shear from 0 to -480 for until the end of the beam. For the moment diagram, we have to consider this thing, that the moment diagram will start from 0, and it will have a positive slope or an increasing slope uh, till this point 6.93 feet, where it will become 0. And from here again it will have a negative increasing or a negative slope till the end point of the beam. You can determine the value of maximum moment at this point by again uh, considering the moments due to this or the change in moment due to this due to this reaction and the applied loading between this 0 and 6.93 feet. This is end of our example. Thank you very much for listening. I hope you have gained something from this lecture. If you are having any questions, please post in the comments.